Okay, this will be the 8.1 notes video on confidence intervals. Um, and let's see, oops, let me get this out of the way here. Let's go back. So basically, confidence interval, of course, is to make an estimate for some sort of unknown parameter. In our case, it will either be a mean or a proportion, just like we did the last chapter. Um, so basically, this little cartoon here, you kind of see the middle there. The temperature will be between 40 below 0 and 200 above, and this guy's never wrong. So if you were to make a really wide interval, you could pretty much guarantee your value is going to be in there, but it's not real useful. So the issue is how confident do we need to be? How big does the interval need to be? And we'll kind of talk about the formula a little bit today. So just again to get back to where we were coming from in the last chapter, we were kind of using known parameters. We would know the true mean or know the true proportion, and then we would determine some probabilities about how likely is it to get a sample of with a certain mean, and that kind of thing. Now what's going to happen here with confidence intervals is it's going to be kind of working backwards. We're going to actually be trying to estimate unknown parameters. And remember, parameter is about a population, so all we will really have is the sample value. You might have a mean of a sample or a proportion of a sample that has a certain characteristic, and you'll use that to estimate the parameter. Okay, so in real life, in practice, it's really much more common to do what's going on in Chapter 8, confidence intervals. Okay, so let's just think a little bit about confidence and just kind of consider an example here. What if we were to rate our confidence on a scale of 1 to 100, and let's say the issue was that we wanted to name a stranger's age within 10 years. So you just look at somebody on the street and how confident would you be you could be within 10 years of their age. And just think about what happens. What if you needed to be within 5 years? Or what if you needed to be within 1 year? Would you be more or less confident as that interval gets narrower? So basically, as the interval gets smaller, to be within 1 year, I'd probably be less confident than I could name someone's age within 10 years. So that's exactly what happens with confidence intervals. The confidence gets smaller as the interval gets smaller. Okay, so again, it's this kind of give and take, like how wide of an interval do you want, but then again, how confident do you need to be? Okay, so let's consider as a little example here, let's say we want to determine the average GPA of all students at our school. Um, so, what would be your first step? Your options are either go ask every single student their GPA and get some sort of census, which might not be too hard to do, but it's in most cases a sample is going to be needed, right? So we would obtain a random sample of students, get their GPAs. Um, if we want to use some sort of normalness in our calculations, remember that magic number of 30 is kind of needed to ensure normality with means here. So that carries over. That's that central limit theorem, and that concept will still apply here. But do you think you're going to get an X bar from your 30 people or so? Do you think that's going to equal mu, the true mean of the whole school? Remember, X bar is just from your sample. So probably not, right? I mean, but that's really the best we can do to get started on this. So really what we've just found, that's called a point estimate. So it's just kind of like a starting point. It's a single statistic for our class. Either it'll be an X bar, like we just talked about, or it could be a proportion, what proportion of the school has over a 3.0 or whatever, some sort of proportion. It's based on sample data, right? That's what a statistic is, and it's just used to estimate the population parameter, either mu or p. Okay, again, we kind of talked about they're not always going to be very precise. There's variation. I could take a sample of 30 and get a certain X bar. I could take a different random sample of 30 and I probably would get a different X bar. Okay, so there's always going to be that variation that we talked about last chapter in the sampling distribution. But a lot of the same concepts, if I were to take every sample of a certain size and plot all of them, that would be the sampling distribution, right? And we talked about how the mean of all of those would be the true parameter value. So that concept still applies, we're just kind of using it in a different way. So what we do is we make a confidence interval. You're going to extend, you're going to have your point estimate, okay, right from the sample, a sample mean, sample proportion. We're going to extend it by adding what we call a margin of error. So you take that estimate, okay, which again, point estimate is the fancy name. We add and subtract the margin of error because again, there's that variation going on, and our estimate probably was not the exact same value as the parameter, but it's the best we can do. Okay, and then so for that reason, anytime you construct a confidence interval, the midpoint of it will always be your estimate. Okay, if you look at the formula just above there, it's the estimate plus or minus some margin of error. So the estimate itself is going to be the center of the interval. So that's kind of a way to make sure you're always doing things correctly. Okay, we talked about confidence levels, you know, how confident you need to be. This is kind of just a statement that you're going to get used to. We are going to say we are blank % confident that the true parameter lies within the interval constructed. And they're going to usually give you a number to fill in that blank. So we'll see how that comes into play in a minute here. But the common levels, a lot of times they want to use either 90%, 95%, or 99%. Okay, but these could be any sort of value. They might give you an 80% or whatever. These are just kind of the three, and there's a certain value that we'll use in the formula for each of these. A hint: the 95% one is right around 2. If you can think about the normal curve and 95% being 2 standard deviations, that kind of thing. We'll talk about that later. But these are the three that we're going to kind of know and use the most. Okay, so let's say this is a really good little diagram. I believe I took this right from the book. So look, if you look up top here, there's an actual sampling distribution of a whole bunch of x bars. Okay, and of course mu is the center because that's the mean of all of the x bars. And then below, if you look and see, there are a bunch of these little lines with arrows, and you see, for instance, right here is a first dot, a second dot, a third dot. Each dot represents a point estimate. So let's say we were to take a bunch of different samples. Okay, so I think there's like 20 different lines here. And then the arrows are extending that by adding and subtracting a margin of error to come up with an interval. And the important one there, the one that stands out, if you look at that one there, so the point estimate was way up here. So maybe our sample was just kind of an odd one, you know, and we got a lot of the higher numbers. And the mean of our sample is really up here. When we extend it to the right and to the left by the margin of error, this whole thing in the circle here, it did not extend through the true mean. Okay, all of the other ones did. So for that point estimate, the interval did not end up containing mu. So that would be a problem where you would actually do all the work, because you're not going to know at the time when you're getting your sample. You might not know that your sample was not really a good one. You know, this was 1 out of the 20 or whatever. Just it didn't happen to estimate the true mean, but all of the other ones did. They all cross over the center line down here where the mean really is. Okay, so for that reason, this one, that's why it's kind of like a 90 or 95% confidence level, because of the 20, maybe 19 of them would have been fine and actually contained mu, but this one did not. Okay, so when constructing a confidence interval, you're never really going to know if your interval contains the true thing you're trying to estimate. So confidence level is never 100%, unless of course you were doing like from negative infinity to infinity or something crazy, which doesn't really give you any information anyways. Okay, so how to interpret a confidence interval? Basically what we want to do here is, let's say they gave you a confidence interval. Let's say a 95% confidence interval was constructed and the true mean GPA, of course our school is higher than these numbers, right? I don't know where I got these from. But let's say they got from 2.0 to 2.8. Okay, so what does that mean? What does that tell you? Okay, and then we'll talk about how to find it later. So what it basically means, is it saying that 95% of the GPAs in the population are between 2.0 and 2.8? And the answer is no. Okay, that's a kind of a common misconception. Confidence intervals and levels don't tell us anything about the population. Okay, if what it does tell us though is this: we are 95% confident that the true parameter, okay, which again in this case is mu, the GPA of the whole school, we're 95% confident that that lies between 2.0 and 2.8. Okay, we don't know how the population, or maybe the population itself may be really skewed, right? So that's why this top interpretation doesn't apply. Okay, we're just 95% confident the true mean lies between those two values. Okay, and that kind of wraps up our confidence interval, the first section, 8.1. In the next sections, we will get more into how do we calculate them.